9 o'clock. I'm going to get started here. So what we'll do today is we'll talk about the homework assignment that was due like at 9 o'clock a few seconds ago. And then we'll go ahead and start to talk about how to represent signed numbers using only zeros and ones. Okay, that should be an interesting topic, because if you think about it, the computer can only store zeros and ones. But how do we represent negative numbers? We use a sign, right? We use a negative symbol to say, okay, this is -5. So the question now is, okay, without a negative symbol, with only zeros and ones, how are we going to represent negative values? Okay, that's the question. And the most obvious answer is to use one bit to indicate whether the number is positive or not, right? 0 means it's non-negative, and then 1 means it's negative. And then the rest of the number will still be represented the same way as we usually do. Well, that may work out okay, but there are a few problems. The first problem is there are 2 zeros, because there's a positive 0 and then there's a negative 0. But there's only 1 0, right? The value 0, there's only 1, but now there are 2 representations, which by itself is not a big problem, but it does use up one combination of zeros and ones, which is not optimal. That's not a big deal. But the biggest deal is, how do we perform addition and subtraction with signed numbers? Okay, that is the biggest deal. Do we need to have specialized adders and subtractors just to deal with signed numbers, or are we going to be able to reuse the adder and the subtractor circuits that we have talked about already? Okay, so those are the things that we'll talk about. But the first thing is to revisit the homework assignment, just to be sure that we understand the solution of those particular ones, and then we'll go ahead and move on. And I'll double check the recorder. Shouldn't have closed the volume control, but it is recording. And this is 310. The homeworks are still in the data and number representation. And here's the logic sim activity. A few people asked me, according to the grading criteria, okay, something doesn't make sense. Well, that's because it's from the previous semester where the question is different. So you still want to turn in your homework assignment the way it's supposed to be done, and not to be confused by the grading criteria. Okay. All right, so the expression is this particular one. You have to apply the negation to A first, and then on the other side you have to apply the negation to B, and then apply the OR to A, the non-negative version, and then do an OR. So there are 2 OR gates and 2 NOT gates altogether. All right, so let's go ahead and do this. And I just picked one of the terminals here. All right, so, and I think I also got one question where Logic Sim does not seem to be working correctly. Well, chances are it is not working correctly. So what you need to do, if you think Logic Sim is doing something that's funky, that's not supposed to be doing, save your file and then close Logic Sim and then restart it. Because occasionally Logic Sim does lose track of the work. So it will mark something as incorrect when it is actually correct, and it will so just go ahead and close and reopen it. Most of the time that will fix the problem. All right, so let's go ahead and get started with what we are supposed to be doing here. We have 2 input pins. One is A and one is B. So I'll just kind of pick these 2, and I'll label these so that we can easily tell which one is A and which one is B. We also have an output, so we'll go pick an output pin and just stick it all the way out to the other side, and we'll just call this output. Out is fine. We just need an indication that this is the output pin and not one of the input pins. And then we take a look at the equation again. So in the equation we have this inner OR, so let's deal with the inner OR first. The inner OR wants A non-negated, but B is negated. There are several ways to do it. I'm just going to use a NOT gate to do everything. So instead of using a bubble at the input of a gate, I'm going to use the NOT operator, or the NOT gate here. This is the NOT gate. So we want the NOT gate applied only to B to serve as the input to this OR gate. And this is the OR gate. and then we can tweak the size of it because we only need 2 input pins, and we can make it smaller so it fits a little bit nicer on the screen. So we have A going in to one of the inputs of this OR gate, and then we have the negative version of B going into the other side. So let's see. So that finishes one of the inner OR gate. The other OR gate, I'm just going to copy from this one. So we'll do a duplicate, and we'll put it over here. Now with this one, the first one is going to take the input from the output of the inner OR, and then the other one is going to be the negation of A. So we'll go ahead and replicate this NOT gate, put it right before the input, and then this time we'll just take a tap out of A into the NOT gate, and that's the entire thing. Well, almost. We have to finish this part here. There we go. So now we have the entire circuit done. Yours may not look exactly like this. If you use a negation on the input of a gate, that's okay too. Okay, it's kind of like a shorthand. But now the next question is, I want to know what kind of combination of values of A and B will make the output a 1. Okay, that's the other part of the homework assignment. This one is a tricky one because it doesn't matter what you do, the output is always going to be a 1. It's a tautology because it is always a 1. The output is always a 1. Are there any questions about this? No questions? It's all good? Okay. Now, can someone prove that this is going to be a tautology even without simulation? If you just look at the equation, if you just look at the expression itself, can you tell that this is going to be a tautology?
Because we have not A and or not B, and
we
so
have
one of those.
Well, the B is not the issue. The issue is we have not A
Or
and
A.
also A itself inside a disjunction. But people would say, but they're not in the same OR. Okay, one is grouped on one side. This negation of A is on one side. This A is not applied to this one. This is applied to the negation of B. But then if you look at Boolean algebra, just like with regular algebra, they also have their own rules, like associative rule, commutative rule, and so on and so forth. Okay? As it turns out, OR is kind of like addition. In other words, you can take out the parentheses and then apply the OR in any order you want. Okay? So by regrouping the negation of A with A and put parentheses around these two, then you will immediately identify, oh, the negation of A or A has to be true. Okay? Because that's one of the axioms of Boolean algebra. So this one is going to be a 1 regardless. So all 4 combinations will give you a 1 as the output. Are there any questions about this? Okay, no questions about this? All right. How many people have taken CISP 440? Okay, so does it remind you of something that you learned from 440? Okay, well that's good. Being able to connect material from one class to another class is always a good thing, because sometimes it will turn like 2 classes into 1.5, okay? It will help reduce the amount of material that you actually have to remember because you're making the connections between the classes. All right, so that's that. So let's go ahead and look at, is the adder homework done, due also today? Okay. All right, so this is the adder homework assignment, and you have to use AND or NOT gates. So when somebody asks me, can we use the exclusive OR gate, the answer is no, because it is stated here that we can only use AND or NOT. Use pins and disable the tri-state. Use nested design. Okay, so we'll make a we'll have to make a half adder, and then we'll make a full adder, and then we have to label everything correctly. So let's go ahead and do this one too. So in LogicSim, I'll just go ahead and make a new slide here. So the first thing I want to do is to make a half adder. So I go to Project, Add Circuit, and we'll just call this HA, or if you want to spell it out, that's fine too. So we'll just spell out half adder here. So with a half adder, It's up to you, how you want to start the construction of your circuit. I personally like to start with input and output pins. Those are kind of like your parameters of a subroutine, so you can kind of tell, okay, we have this kind of input and that kind of output. Then you start to think about, okay, but how do we connect the input and output? But that's a personal thing. You can certainly do it, other ways as well. So we'll go ahead and make all of these input output pins first. And we'll label the first one, let's see, in my description here. Okay, so the two numbers to be added will be A and B. So I want to label these, accordingly. So I want to label this A, and I want to label this one B. This part is optional. You do not have to do this. The output pins are more important because one is the result, which I'll call R, and then the other one is the carry, which I'll label C, or if you really want to be clear, you can label it C out, because later on we'll have a C in when we deal with a full adder. Okay, so that's entirely up to you, how you want to label your pins. I personally just like labeling all the pins first, because this way it helps to identify, what needs to be done, and then I will think about how to do it. Okay, all right. C out is the easy one. Okay. The carry out is a 1 if and only if both inputs are 1s. So an AND gate would do nicely over here. So we just have to change this to a 2-input AND gate. The output goes straight into the carry out, and then the inputs would be coming from A and B, non-negated. So that's my carry. The result is a little bit more, involved, because you cannot do exclusive OR. Now, if you cannot do exclusive OR, you kind of have to spell it out. Now, to spell it out, you have to rely on 3 AND gates, or 2 AND gates and 1 OR. Okay, so we already have 1 AND gate with 2 inputs, so I'm just going to replicate it here. Control D. Here we go. And Control D the other one. And then we need an OR gate, to combine the output. And I'm going to change the shape first before we put it in place. Okay. So the output is coming straight out of the OR gate, and the input and OR gate are coming from the AND gates. So we'll go. Not exactly the best artwork, but functionally speaking, it's okay. So we'll just move these things around here. Now, to look at my own homework assignment, it says to use AND or NOT gates. Does it say anything about using a bubble, as the input of a gate? Okay, if it's not explicitly allowed, I'm just going to make the assumption that it is not allowed. Okay, even though it is. Okay, but I just read off of my own homework assignment, and I just want to play it safe. So since it is stating that we can use a NOT gate, I'm just going to use a NOT gate instead of a bubble. Bubbles are nice because they make your design more compact and easier to read, but I just want to stay on the safe side, which is not too much of a problem, because we just have to do something like this. Okay, so it's not a big deal. Okay. All right. So now we'll use A to feed into this negation here, and A is going to be non-negated, feeding into the input directly into the conjunction here. This one is going to be B non-negated. So we'll put it down here, and then the other one is going to be B negated. All right, so I think I got the half adder done already. Okay, so the next step we have to do is to test it. Okay, you always want to test and make sure that it does work. There are only 4 possible cases because there are only 2 input pins and they are independent. So that means when A is a 1, B can be a 0 or 1. When A is a 0, B can also be a 0 or 1. So we have 4 distinct cases. And from the truth table that we talked about in class, you should know what should be the output for each one of those 4 test cases. So we'll go ahead and test it. Okay? A 0 plus 0 has a 0 as a carry and a 0 as an output. As a result, that's correct. When one of them is a 1, the output is a 1, but if the carry is a 0, that's correct. And the flip side, symmetric, okay? So the only really tricky case is when A is a 1 and B is a 1, then the carry should be a 1 and the output should be a 0. So we do it here. So now I have just verified every single case for a half adder. Do we have any questions at this point? Okay, so with the half adder done, the next thing we have to do is to right click on the design itself to edit circuit appearance. So the way it looks is like this right now, which is okay. It's not a problem. It just looks kind of confusing because I can see there are two inputs, but which one is which one? There are two outputs, which one is which one? I personally just like to do it like this. I would put a label for the entire design itself, a half adder. Okay. You don't have to do this part either. I'm just, saying this is a good idea to, this is something nice to do, just document the whole thing. Okay, so here's A. And what I just did was to replicate the label, because I can always change it. So I think, yep, I guess not. I thought I can change the label. Maybe. Does anyone know whether there's a way to change the label?
Yeah.
Yep.
No, I think you just have to delete it.
Yeah, I think so too. But that's okay. It's not a big deal. Okay. It only takes a few seconds. Okay, maybe 30 seconds to properly label all the pins. But once you label all the pins, then there's no confusion, especially between the R and the C, because they're both outputs and they're not symmetric. So now that we have the sub-circuit looking like a chip on its own, we can now utilize it in the full adder. So it's time to create the new circuit, which is our full adder. So we'll call the circuit full adder. And the full adder is going to make use of the half adders. Once again, we have to identify the input pins and the output pins. Okay. So the input pins, there are 3 input pins in this case. Okay, this is the second, and that's going to be the third. We can always space them out a little bit here. The first input pin is A, which is one of the numbers to be added. B, the other number to be added. And there's one extra one, which is the carry in from the less significant digit. So C in is the third input pin. Are there any questions about why there are 3 pins or 3 input pins with a full adder instead of 2? Okay, no questions? Okay, so let's identify the output pins. The output pins, the first one is just going to be the result here. So I'm just going to label this one as R. And the other one is carry out, okay, because we need to send the carry to the next column. So this is C out. So now the question is, how do we work with the input pins so that we have the output pins? The carry is the one that is a little bit more complicated. We'll deal with the result first, okay? Well, since we have the half adders, they must be useful in some way, right? So we'll go ahead and put one half adder here, and just from the naming of the labels, you probably can guess which A should go where and which B should go where. Okay, so that's a little intuitive, just right there. Okay, so the 2 numbers to be added, they will feed into the first half adder. Okay, well, because it's called a half adder, that means we need another one. Okay, so now the question is, what do we put into the second adder? What would be the input to A? What would be the input to B? And the result, we kind of know that the result here goes to the result output here. But how do we connect, A and B of the second half adder? When you look at the way we do the calculation in columns, you will understand that the result of the first half adder becomes a part of the input of the second one. Now, since addition is symmetric, I can connect that one to B. It would not, be a problem. Okay. When you deal with a subtractor, it is no longer symmetric and it becomes important which one connects to A and which one connects to B. So this is just a reminder of your subtractor homework assignment. Okay, what about B?
C in.
B comes from C in, that's right. All right, so now we are pretty much done with result. And you can test the circuit just the way it is right now, but you cannot test C out because it's not connected. Now we have 2 output pins, one here, and yeah, 2 outputs here, but we can only have 1 output pin out of this entire sub-circuit. So the question is, how do we combine these two? We talked about this in class as well, okay? If either half adder is giving you a carry of a 1, the output has a carry of a 1. So that means it's just a logical OR. So we'll grab a logical OR gate. And, oh, there's an AND. OR. And turn it into smaller design. And connect one carry to one of the inputs and the other one to the other one. So now we have the full adder. Before we turn it into a component and actually use it, it is a good idea to test it. So we'll go ahead and test it. This is one test case already, right? 0 plus 0 with an input of 0 is going to give you a 0 as output and no carry. Makes perfect sense, okay? So we'll test all the cases with carry in being 0 first. Okay, that's correct. That is correct. And that is correct as well. Okay, now we'll test with the carry in being a 1. If carry in is a 1, but both numbers are zeros, then you have a result of a 1 and a carry out of a 0. That's correct. If one of them is a 1, then you have a carry out of a 1 and a result of a 0 because it becomes just 1 plus 1. So that makes sense too. That makes sense too. So now here's the last case, which is 1, 1, and 1. And this is the only case where you end up with a 1 as a result and also a 1 as the carry out. So I have just verified that the full adder circuit is also functioning correctly all by itself. Are there any questions about the full adder subcircuit? Okay. Now I did not do one thing that I'm supposed to be doing. What did I not do that I should be doing? It's just a good practice. It's not wrong not to do it. It's just a good idea. What happens if there's a power fail right now?
Oh yeah, you didn't say.
I would have lost everything, right? So it's a good idea to save, just occasionally, every time you verify or validate a particular design, save it, okay? Because that way you won't lose it in case there's a problem. Edit circuit appearance, same thing as last time. This is not a typical way to look at a full adder. You can kind of tweak things around a little bit if you want to. I'm not going to spend too much time, but I do want to increase the spacing between the pins. So what I'll do is I'm just going to do some minor editing here. Make the rectangle just a little bit longer, and so I can space out the input pins. Put this one here. This one. Well, it doesn't look very good, but it'll be fine. But the most important part is the label, okay? Because this is A, this is B, this is carry in, this is our result, and this is carry out. This way, when I make the final circuit, I don't have to think about, okay, but which pin is which pin. There we go. So now it's time to go to main and start to use our full adder. So to make your full adder, you just go to your full adder here, and we'll have to slap 4 of these things. So we'll just duplicate, copy, duplicate again, and now we have 4. And then the next thing we have to do is to give it a lot of pins. Well, this is not the smartest way to do it, is it? Okay. Because then I have to make a lot of replication of the pins as well. So I'm gonna do it the other way, which will save me a little bit of work down the line, which is to give it all the pins first. Okay, so 1, 2. The carry does not need a pin. Okay. Well, not in a daisy chain fashion. The result does need a pin here. I do not want to do the labeling because I cannot change a label. Let me see it. Can I change that label? Yep. This one I can change, but not in the appearance of a subcircuit. So that way, it actually does make sense to make all the labels here too. So we'll go ahead and do it that way. All right, so according to the documentation, this is important because we want to use the documentation here. 4 input pins designated A3, A2, A1, and A0 for the 4 bits of the first number, and then B3, B2, B1, and B0. And then the output pins are designated D for the sum, okay? So we'll go ahead and create all those labels first. So one is A, this is A0. We can change the 0 later on, this is B0, this is going to be D0. Go. All right, and just have to move the whole thing a little bit to the right. There we go. Line things up a little bit so it look nicer. There we go. All right, so I'm gonna make the connections now before I do the replication. Okay. Go. All right. So this is as far as I can go, without, making special cases for the other subcircuits. So I'll make 4 or 3 additional copies of what I see here. And it helps to zoom out a little bit because otherwise I cannot fit all of them on the screen. So we'll do a duplicate. It's complaining about this one. Oh, that's because C in is not specified yet. That's okay. So duplicate one more time, and now we have the entire design. Okay. Well, it's almost there, but we are not done yet. There are a few other things to tweak. C in for the least significant bit is supposed to be what? 0. And I did mention in class how to specify a constant 0. So this is not supposed to be a pin. It is supposed to be a constant 0. So you pull a constant out of the tool and just stick it here, except you have to change the value. Instead of 1, you have to turn it into a 0. And that connects to the input pin of the least significant digit. And then the carry output of the first one goes to the carry in of the second one. Now, the way I designed the circuit doesn't lend itself to a nice picture, but yeah, I can get the job done. It just doesn't look very good. The best way to do it is to put the carry out here and the carry in here. Then it's just one straight line from one full adder to the next one, right? But I'm not an artist, so this does not bother me at all. It might bother Julia though. Does it bother you that I have all these lines going all the way around? No.
As long as it's nice enough.
All right, so we'll go ahead and do this. And this is the last one. And we have one final carry out from the last full adder because that pin is actually important as well. So we'll have one extra carry out pin that we attach here. And this is the carry out of the entire adder. But I'm just going to label it as just C out also. And it's time to adjust all the other labels. So we'll go ahead and adjust these guys, turn it into a text tool. And you can, this one is okay. This is A1, B1, A2, B2. Oops. Are there any questions about this whole process of making your full adder? No questions? And obviously the D's have to be modified as well. D1, D2. Now we have to think about test cases. Okay, the design is almost done. I'm just finishing up the documentation part of it. So let me just double check with my own notes here. One output pin designated C as the final carry bit, not borrow. So we'll go ahead and change this one just to be consistent. Okay, if the homework assignment calls for C, I'm just going to use C all by itself. There you go. All right. So now the full circuit is done, I have to test it. Now obviously in this case we have 2 to the power of 8 actual input test cases. Well, but since I already know the subcomponents are working, I don't really need to use all 2 to the power of 8, which is what? 16 by 16 is 256 test cases. Now that's a lot. I mean, it's not necessary at this point to test all of those. So I'll just go ahead and test out some representative ones. 1, 1, 1, 1 plus 1 should be 0, 0, 0, 0 with a final carry of 1. Okay, good. We'll go ahead and test them. Okay, so we'll go to simulation mode. A is going to be the 1, 1, 1, 1, and B is going to be the 1. Now remember, B0 is the least significant bit, so we put a 1 here, and all the outputs are zeros except there's a final carry of 1. So that worked out okay. That's correct. We already tested 0 plus 0 because that's the default. Okay, so that one is tested already. I'll just test one more, which is 1, 0, 1, 0 plus 0, 1, 0, 1, which should end up as 1, 1, 1, 1, but no carry. So we'll tweak the top number to be 1, 0, 1, 0. The bottom number to be 0, 1, 0, 1. The output is 1, 1, 1, 1 with no final carry. So I'm fairly confident this is actually working correctly now. Okay, but that's only because I also tested each subcomponent, completely. So the final test is not complete; it's just a spot check. But with each subcomponent, I did test each one completely. All right, so that's it. Are there any questions about the design itself or the process, other than artistically it doesn't look very good?
Symmetric.
It is symmetric, but in terms of, I could have made the carry in the carry out aligned a little better, so it doesn't have to go all the way around like that. But other than that, okay, are there any questions? No questions? Okay. How many people have taken at least one class from electronics, from ET? Okay, so do you guys know that you can actually buy 74 chips or 74 family, they call it jelly bean, parts, and they can implement AND gates, OR gates, NOT gates, and so on, right? So you can actually make your own 4-bit adder if you want to, using a breadboard. On a breadboard, so how do you specify zeros and ones on a actual circuit board? Switches. Okay, you just use toggle switches and a pull-up resistor. Okay, so when it is not connected, it is a high. If it is grounded, it is a 0. How can you see the output of the entire thing? LEDs, right? Okay, you just use some low current LEDs, and you can actually see the entire thing. So you can flip the dip switches, or not dip switches, but the toggle switches. You can specify the input, and then you can look at the LED as the output. Okay, it's not a bad thing to do. I think it is really kind of a neat thing to do, just to see that, oh, I can actually do this on a circuit board using what we call jelly bean parts. All right. Any other questions? See, I wish when I took this class, many years ago, I was actually taught, these low-level stuff, and people give me a circuit board, a breadboard to play with. That would have been fun. All right. So if there are no questions about this, I'm going to leave this one on the screen for now, and instead we'll continue with our discussion. We are pretty much done with addition and subtraction. So what we're going to do next is to move on to 2's complement. How do we represent negative values? Well, we are in von Neumann. Let me see, what else do we have to talk about here? We talked about memory bus operations already from last time. Okay, you guys do you still remember how to interface with a memory chip? Sort of, kind of. Okay, look, we'll go ahead and take a look. Okay, I actually saved that design so I can reuse it today. So RAM example, there we go. All right, so this is what we had last time. And let me see if you can still remember how to make this work. So what do I have to do if I want to store a, let's see, I want to store a 7E at this location. What do I have to do? All right, so let's check out what we have to do, and I'm going to write it down using mouse pad. That's kind of my oops, not this one, mouse pad. That's kind of my whiteboard, but it's recorded. Okay. All right. So we want to store a value of 7e in hexadecimal into the location that is appearing in red right now. It's highlighted. Okay. So it's a write operation. Okay. Remember, when we specify a read operation or write operation, they are specified from the perspective of the processor, which is invisible in this case because you are the processor. You are the one who is controlling the memory bus, okay, and try to specify the correct values of all the different pins. Are we doing okay so far with that assumption? You are the processor, we are the processor, okay? We are trying to specify the operation. Okay, so first thing we have to do is to find out the address, the logical address of that one location, okay? So the logical address is going to be what? What is the address on the chip itself? What can you tell? Okay, 0, 1, 2, 3, 4, 5, 6. This is location 0, 6 on that particular chip. Okay. So the first one is 0, 6. This is hexadecimal 6. But that's just the location on that chip. What is the logical location from the perspective of the processor? If you look at the memory chip, how many locations can each chip store? Well, it doesn't tell you directly, but it does tell you a hint because it tells you what is the width of the address bus. What is the width of the address bus? 8 bits, okay? So if you have 8 bits to specify the address, how many unique locations can be identified? 256 because it is 2 to the power of 8, okay? So that means the first chip, RAM 0, has 256 locations. The second chip also has 256 locations. The red rectangle is on the second chip, so that means this is location 256. Okay, I'm going to use a mouse pointer because otherwise, when you watch the recorder, it's not going to be it's not going to be very helpful. This is at logical location 256 because we start counting from 0. That's why it's not 257. So this is 256, 257, 8, 9. This is 260, 261. This is 262. But that's in decimal. I don't like decimal numbers, right? Okay, so let's count it again, but this time in hexadecimal. This is 100 in hexadecimal, 101, 102, 103, 104, 5, 6. So the way you do the calculation is 6 plus 100 in hexadecimal, and that will give us a hexadecimal number of 106. Next question. This is a hexadecimal number. How do we specify that number as a binary number? Because the address bus pin is specified in binary. It's all zeros and ones. What is a 1 in hexadecimal in binary?
0 to the 1 power.
Is 0, 0, 0, 1. Okay? Now, it's not just 1, because 1 hexadecimal digit corresponds to 4 binary digits. So the leading zeros are actually important in this case. Now, whether we drop those later on, that's a whole separate question. Okay? So we want to convert this into a binary number. Okay, so that is 0, 0, 0, 0, 0, 0, 0, 1 for the 1, 0, 0, 0, 0 for the 0, and then 0, 1, 1, 0 for the 6. That is the binary bit pattern. Are we doing okay so far with the binary base 16 to base 2 conversion? It's just a table lookup. But the memory bus is only 9-bit wide, okay? It's only 9-bit wide, which means we only pay attention to the least significant 9 bits. These are the bits that needs to be put into the input pin all the way up here. So that's how we're going to do it, okay? So, so that's going to be 1 here, and then 2 ones over here. Voila. Okay, did you guys see the location just got highlighted? Okay, that's because we specified the right address already. The decoder is doing its job as well. Okay, it's taking the most significant bit out of the address pin and then use that to turn on the correct RAM chip by activating the right chip select. Are we still doing okay so far with this exercise here? Okay. So the next thing we want to do, going back to the mouse pad here, is to specify the right operation. Okay. A right operation means the load operation needs to be a 0. Okay. Which it is already. Okay, because if we look at all the input pins, by default they're all zeros, so we are already specifying a right operation. That's good. I said that I want to write a 7E into that location. What is a 7E? Well, let's take a look. In hexadecimal, 7E is in binary. What is 7 in 4 bits? 0, 1, 1, 1. Very good. And what is E in binary in 4 bits? Yep, 1, 1, 1, 0. There we go. So that would be the pins that I need to specify in the data pins. So that would be this guy here, and I have to reattach this pin, by the way, because otherwise, there's no way to actually specify the content on the data bus. So once I have specified that, we'll go ahead and specify the values: 0, 1, 1, 1, and then 1, 1, 1, 0. There we go. Oh, but nothing is happening. Well, nothing is happening at this point because the RAM chip does not change its content. Even if you specify the correct address, the correct data pin, and specify right operation, it doesn't happen because you need to have a clock transition. Now with this particular one, it specified that it wants a low to high transition on the clock line. The clock line has a low at this point because it's a 0. So the moment I change the clock line to 1, the content will change. So observe the highlighted location here. It's 0, 0 at this point. Click. Now it's a 7E. So this is how you specify a write operation, just to write a single byte to a certain location in memory. How many steps do we go through? Quite a few, right? Okay. And this is actually how the Pentium processor or your i5, i7 processor has to go through in order to write to memory. It's really quite tedious. So now the next question is, well, that's kind of slow. Can we speed it up? How would you speed it up? Well, first of all, do you want to speed it up? Why do we want to speed it up? Now, if your processor is really slow, you don't need to speed up the access to memory because the processor is going to be the bottleneck. Is that the case? How many cores do you usually have with a semi-expensive i5 processor, which is not even top of the line?
4 cores.
4 cores, okay? With 4 cores, it means it has basically four full processors, okay? Within each processor, how many calculations do you think it can go through at the same time? In other words, how many ALUs or arithmetic logic units does it have per processor? 1, so it can do only 1 calculation at a time. 2, 3, how many? I don't know the actual answer either, so we'll go look it up. Okay. So one thing, something you really should learn from any class is how to find information on your own. Okay. Because most material will be out of date by the time you graduate. So if you only rely on information or knowledge that you learn in a class, you'll be outdated by the time you graduate. Okay, I know it sounds really depressing. On the other hand, if you learn how to learn, then you can never be outdated because you know how to refresh yourself to get the most up-to-date information. So all you have to do is to Google, okay? This was not available when I was in college. There's no Google, there's no internet when I was in college. There were modems at 300 BPS. 300 BPS is 300 bits per second for those of you who thought you misheard me. Yes, 300 bits per second, not 300 megabits per second or even kilobits per second. It's actually 300 individual binary digits per second, which usually means you're translating that into characters. it will take about 10 bits of time to transmit one character, okay? Plus or minus a little bit, okay? So 300 bits per second means about 30 characters per second. So most people can read faster than your modem can receive or transmit. Yeah, but I got this 2 megabyte file to transmit. How long would it take? We'll do some calculations here just for comparison, okay? So you have a 2 megabyte file and the transmission speed is 300 bits per second, okay? Okay, let's try to do some equalization of units here. 300 bits per second is approximately 30 bytes per second and 2 million bytes here. That's how much time, how many seconds it will take to transmit a 2 megabyte file. Assuming there's no error and retransmission. Okay? So we'll just go through the whole calculation here. So we have 6. Okay, so we have about 67,000 seconds. How many seconds do we have in an hour? Well, there are 60 seconds in a minute, and there are 16 minutes in an hour, so there are only 3,600 seconds in an hour. How many hours are we talking about? Too many. Yep. It's how many hours do we have in a day? Multiply this by 24, right? So this will be done within a day, assuming you don't have any, tragic, error bits and whatnot. So we have to be retransmitted and stuff like that, which happens all the time because the phone line is not exactly it's not a very good way to transmit data. So that's why when I was growing up, there's no Google. Okay, even if there's a Google, it's not useful. All right, so we'll look up what we were looking up before. Okay, i5 ALU per core. Okay. So here's the i5 processor. I'm just doing a quick run here to find out what would be the best document to look through. Yeah, that's all fluff.
I think it says right there.
Oh.
Intel uses 3 general purpose ALUs per core.
Oh, right here. Let's check that. Okay. Well, it's okay. Let's see. 2 ALU AGU, 4 execution units. That's for the AMD design. And then the Intel design has 3 general purpose ALUs per core. So that means it can carry out 3 calculations or 3 additions at the same time. They're all in parallel. Okay. So there's some extra time you need to do, like decoding instruction. We'll do all that with the test processor too. So there's decoding, execution, fetch, and then store result. Okay. But basically, what this means is your processor can pretty much keep up with 1 instruction per clock. With a 3 gigahertz processor, if the instructions are timed correctly, it can perform about 3 billion instructions per second. That's a lot. Now the question is, how fast is your RAM? Okay. Well, let's look up your RAM specification. So we can go to UA or any website that sells RAM, because we just need to look at the numbers. That's all we need. Look up computer hardware, memory, desktop memory. I haven't shopped for a long time, so this is actually, wow, that's not too expensive. Doesn't sound expensive to me. Okay, so the timing, what do you think these numbers mean? the 9, 9, 9, 24, and the 2n. What do they specify? Nobody knows. Okay, how do you know you just got the right kind of RAM for your computer? What happens if you get the wrong kind of RAM for your computer? What if you get RAM that is slower than you think, but you program your BIOS, saying, oh, these are fast, fast RAM. What happens?
You get an error.
Well, if you're lucky, you get a consistent error. If you're not lucky, the computer will work when it's cold, and when it warms up, it will die. It might do some data corruption first before it dies, like corrupting your hard drive along the way and stuff like that. But it will die. Okay, it's temperature dependent. Okay, what is going on here? What are these numbers? Okay, the latency time has to do with how much time does it take for the address bus to stabilize. How much time does it actually take to write? How much time does it take to read? So there's a delay along each and every step. Okay? Are we doing okay so far? Every time you change anything on the memory bus, okay, it takes time for that effect to become recognized by the memory. Okay? So if I just go back to the diagram here, okay, every single step that we did, okay, changing the address bus here, remember, who is driving the address bus? Who is specifying the content on the address bus?
CPU.
The processor, right? The CPU. So the processor, at a certain time, it will say, okay, I want to look at location, this is 106 in hexadecimal. The question now is, how much time does it take for the decoder circuit to do its job? And how much time does it take for the RAM chip, the correct RAM chip, to say, oh, you want me to get to location 6. There's a delay. Okay? So the numbers that we were looking at, each number is corresponding to one stage of what you need to do to work with a memory bus. Are we doing okay so far? And those are in nanoseconds. Okay? What about changing the load line? Okay, if this is originally a 1 and we turn it into a 0, it would take time for the RAM chip to respond and go, oh, you want a write operation, okay? I'm going to switch gear and prepare for a write operation. What about the clocking one? That is the most significant one, okay? Because the clocking, when we transition clock from 0 to a 1, that's from the processor's perspective. Does the RAM chip actually respond instantaneously? Nope, it does not. It takes a certain amount of time for the RAM chip to sample the data line, copy the content on the data line into its content. It takes a certain amount of time. Is that okay so far? So that's basically what is determining the speed of memory. Okay? Now let me ask you the next question. What if I would change the next location? Okay, the next one, which is location 107 to 21. What do I have to do? I have to readdress the address bus, right? I have to change the address bus so that it will go to the next location. And then I have to change the content that I'm writing to it. What did I say? 2-1. Okay, so we'll specify a 2-1 here. This is 2, and this is a 1. And then I have to clock again, right? Change the clock, going back to 0. That is how much work is involved to write to a location that is right next to the one that we just wrote over, that we just overwrote. Okay? Does it sound a little redundant to you? If I want to overwrite the next 32 bytes, I would have to change the address bus every single time. That seems kind of redundant. So what do you think people do instead with DDR? What is DDR, by the way? Damn doctor.
Dynamic.
No, it's double data rate. Double data rate, okay? Okay, but how does it work? What is one trick we can use to speed up this access, the memory access, when you are accessing sequential locations? Okay, the next one, and the next one, and the next one, and the next one. What do you want to do?
Increment.
Increment, exactly. So what you want to do, I cannot show it here because they don't have the actual, component here. We can make it out of basic components, but it doesn't have it here. So what you want to do is to make your RAM chip a little bit smarter. So the RAM chip will now have more control lines. And it will also have a more complicated circuit on it. Okay? And you can basically, the processor can say, you know what, I want to get into burst mode for the next few operations. So the burst mode is now specified using its own dedicated signal line to specify, okay, this is a burst mode operation. So with a burst mode operation, what happens is only specify the address once. This is the start location. And then after that, every single time you clock, the RAM chip understands, oh, we're moving on to the next location. So you don't have to clock out the address bus every single time. And that saves time, okay? What else can we do to speed up this operation? Okay, now remember, even with a counter on the RAM chip itself, you just need to increment the counter every time you do a low to high clock transition. It saves you time because you don't have to re-specify the address line anymore, and that saves quite a bit of time. But it's still kind of slow because when the clock goes from 0 to 1, we have to go back to 0 before it can go from 0 to 1 again. Does it make sense? In other words, if you do a time plot of the clock line, it goes like this, right? But the change of the RAM content can only happen here, 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 and so on. So what we can do is to say, oh, let's also pay attention to the falling edge. Okay, so in burst mode, the RAM chip will go, oh, we'll do updates whenever there's a rising edge and also whenever there's a falling edge. But now things get a little dicey because the processor now has to go, oh, we'll set up the data line safely before the rising edge of the clock line. So this time is what you need to do, it's the only amount of time you can do to specify the new data on the data bus. Because you need this to be done way before the rising edge. Because if the rising edge happens and you are still specifying the data bus, the RAM chip can clock in or store the wrong data because it's not done yet. The data line is still there, they're still changing. Are we doing okay so far with that concept? Same thing at the falling edge. So within a certain amount of time before the falling edge, the data line has to change and settle before the falling edge when the RAM chip is sampling. Okay, are we doing okay so far with that? So what about the amount of time the RAM needs to store, needs in order to store the content? That will be the time from an edge to the next time the data line changes again. So during that time, you kind of have to freeze everything on the data bus because the RAM chip is sampling the data bus and go like, I will take whatever is on the data bus to change the content of my chip. Is that okay? So all of these timing is very, very important. And that's why when you look at a memory chip, a module, a DIMM, they come in all of those numbers. Because each number is specifying a particular part of the timing requirement.
So what does the 99924-2N?
You have to look into it. The numbers are specified, or they're okay. If I look at specification, that might actually give us the detailed information here. So click on timing. It's not. Okay. Well, let's just open up a new tab here. DDR. So we'll use an older standard. So to make it simpler. But my computer has hung up. The browser has hung up, I should say. Let's kill it. Now it's really frozen.